let's think about some Bootstrap samples. And I want to do this in kind of an abstract way. So here's my original sample. It had values Y, W, D, O, and L. I want to know if the following are possibly Bootstrap samples. So I'll show you with the first one how I would determine this. First, I would look, how many data points were in my original sample? 1, 2, 3, 4, 5. So certainly a Bootstrap sample needs to have 5 observations. So this first one, 1, 2, 3, 4, 5. Okay, so it's the right size. And then I want to look and see if all of the values in the possible Bootstrap sample appeared in the original sample, because we're sampling from the original sample. So Y appeared in my original sample, W, it looks like I got Y twice, D appeared, O appeared. So this one is a possible Bootstrap sample. I'd like you to think about the other 3, and we'll talk about them for synchronous class. So some terminology here. The Bootstrap sample, that's the random sample of the same size as the original sample, sampled with replacement from the original sample. Then a Bootstrap statistic is a statistic that's computed using a Bootstrap sample. And a Bootstrap distribution is the distribution of many Bootstrap samples. So I think I'm just going to put in that same screenshot again, and then let's think about these things. So here is one Bootstrap sample. One Bootstrap sample. Then this number here, that is a Bootstrap statistic, because it's a statistic computed from the Bootstrap sample. And this is my Bootstrap distribution, because it's a distribution of many Bootstrap samples. So if you remember, the sampling distribution, if we were able to take repeated samples from the population, the sampling distribution would be centered at the population parameter. In contrast, our Bootstrap distribution is centered at the sample statistic. So that's not the most convenient. But luckily, the thing that we really care about with the distribution is the variability. So we can estimate the standard error of a statistic by using the standard deviation of the Bootstrap distribution. So basically, we're going to use our Bootstrap distribution as our sampling distribution, and then we can compute the standard deviation. And remember, the standard error is just a special word for the standard deviation of the sampling distribution. And maybe I'll stick in my screenshot one more time, because actually StatKey will give you that standard error. So it will compute the standard error, which is useful for you if you're trying to make a confidence interval. So I think I've been showing you mostly how to do bootstrapping for a difference in means. I was doing that tug-of-war team, but I also was talking about a single proportion with my M&Ms, and we can use bootstrapping to estimate the standard error and or to find a confidence interval for basically any parameter. So for a single proportion, difference of proportions, mean, difference in mean, standard deviation, correlation, lots more parameters. We can do inference this way. So the procedure for the bootstrap is basically step 1. You don't necessarily need to do this, but I think it's a good start to record the observed value of the sample statistic, the real sample statistic from your real sample. Then you take a bootstrap sample, sampling with replacement, the same size. Then you compute the bootstrap statistic and write it down somewhere. And then you're going to do those steps 2 to 3 a bunch of times, 1,000 times maybe. You saw me being lazy and clicking the 1,000 times button on StatKey. And then we're going to look at the distribution of bootstrap statistics. And we could either just look at the middle 95% and use the 95% rule, or we could be more accurate and look at that standard error that StatKey computed for us and use that with our statistic plus or minus 2 times the standard error formula to come up with a more accurate confidence interval.